All right, here is an example on the computation of IXY in a simple section, which is a Z shape. I've taken this one in particular from the text, so I'm just going to explain to you in the way that we've done it how the calculations are. We want to find IXY, right? So the x-axis is this, the y-axis is this. So this is the product of inertia about those axes. Nothing about rotation yet, just get the IXY. So the section is 90, 90, and 200. And 15 is the thickness of all the plates. So they are millimeters, but I've left the units out. We are being consistent. Because this thickness is 15 and this is 90 total, so this is 75, that is spread out. And it's the same both top and bottom, right? So here is the table that I use to calculate IXY. I begin here by writing what the dimensions of my blocks, my pieces are. So I'm going to use this number 1, which is a 75 by 15, a number 2, which is the whole vertical one, 200 by 15, and the bottom one, which is also a 75 by 15. Now, the areas of these things go here. So 75 by 15, I didn't get it, but 75 by 15 is 1125. So I get the areas of my pieces. And 200 by 15, that's 30,000, right? 3,000. Now, I now calculate where are, well, okay, the IXY of this block, okay, about its own centroid is 0. Because this is a symmetrical shape, right, with two axes of symmetry, and these are the principal axes of that block, right? Therefore, the IXY of piece 1 by itself with respect to this axis is 0. Therefore, the contribution of this square to the IXY with respect to this axis is the parallel axis theorem. So I have to take this area and multiply it times the two shifts. What are the shifts I need to make this go to here? I need to slide it to the right, and I need to slide it down. Therefore, I need to slide it to the right 45. You can calculate half of 75 plus half of 15. And I need to slide it down 92.5. Because this is 100 and I got to take 7.5 off. So the second piece, which is the vertical one, has its centroid coinciding with the XY axis. Therefore, I don't have to shift it at all. And the third piece, which is here, it's exactly the same as this one. It also has its centroidal axis here. And in order for me to shift them to here, I have to shift them to the left and up. Therefore, I have to shift them negatively and positively. Now, as we have from the formula for the shifted is equal to the area times the shifts plus the IXY about the centroids. So we take our areas, multiply it by the shifts, get this, get our area multiplied by the shifts, get this, get our area multiplied by the shifts, get this. Add this 2, that's this part, and the centroidal, in this particular case, not always, but in this particular case, because these are symmetrical by themselves, these are IXY is equal to 0, so we have 0 on this part. Adding this and this, we get 9.36 times 10 to the 6, which is the polar moment of inertia of this cross-section about the centroidal axis XY, okay? Negative. Now, the next thing would be, what is the angle of the principal axis? Well, for that, we need to calculate, in addition to IXY, we need IX and IY. Now, IX and IY are standard computations. which you have done repeatedly, and I am sure that you can do. And I would suggest at this point, you could stop the video and calculate, right? That is, use it as a practice. This is a section. What is the I about this axis? What is the I about this axis? And you should get that IX is 2929 times 10 to the 6, and IY is 567 times 10 to the 6. Once you know IX, IY, and IXY, then you can calculate what is the orientation of the principal axis. The formula is the tangent of 2 theta is equal to 2IXY, right, divided by IY minus IX. So 2IXY is 2 times 936, which is 1873 negative, and IY minus IX is minus 23.62. The two negatives cancel, and the ratio becomes 0.79. That means that the tangent of 2 theta is equal to 0.79. Therefore, the arc tangent of 0.79 is 2 theta, and we find that it is 0.67, from where theta, this is in radians of course, is half of that of 0.33. Passing that 0.335 radians into degrees, multiplying by 180 and dividing by pi, we find 19.2 degrees, which means that the principal axes are these, and they are rotated counterclockwise 19.2 degrees with respect to the x-axis. Okay? So that's that example. Let me consider a second example briefly in which this is not true, that IXY about the centroids are all 0. Okay? Let me pause and do that on the next batch.